plus 5x squared and minus 6x and minus 4. All I have to do is go to second table and plug in -2. If it's 0, it's a factor. Nope, it's not a factor. The answer is -4. F of -2 is -4. Therefore, x plus 2 is not a factor of the numerator of f of x. It's not. Any questions? Are we okay with this? Moving on. Can we move on? Do we need more examples? Anyone, please? Do we need another example, or are we okay with this? With the factor and the remainder theorem? The remainder, yes, of course. Of course. Let's choose.
35.
35 it is. Good, 35. In 35 we have f of x equals 3x cubed minus 7x squared minus 2x plus 5. And they want us to investigate f of -3. Which means what they want is us to look at this division over, can anyone tell us over what?
X plus 3.
Indeed. If this happens to be 0, then x plus 3 is a factor. If it is not 0, then x plus 3 is not a factor. Chances are that because of 3 and 5, it cannot be a factor. But let's see. Good. We punch in 3x cubed minus 7x squared. Good. That's not the minus I wanted. Good. And minus 2x and plus 5. Good. Again, 3x cubed minus 7x squared minus 2x plus 5. And all I want is to plug in -3. Okay, the answer is -133. So f of -3 is -133. Therefore, x plus 3 is not a factor of f of x. Any questions? Okay. Now, part of all this is needed in the next section, which is 3.5. So we talked about all polynomials. We talked about the remainder and the factor theorem, long division, synthetic division. So now we finally get to rational functions. I want to say that these are the most involving functions. They have a lot of steps to look at, a lot of important information to gather before we graph. One thing that we have never seen before in polynomial functions, they don't have this, are something called asymptotes. Asymptotes. there are three different types. We have never seen this before. We have never talked about this before. There are three different types. Horizontal, vertical, and slant, oblique, in other words. Horizontal, a line like that. Vertical, a line like that. Slant, either like this or like this. What are they? Okay, an example of each. However, I need to mention from the very beginning, horizontal and vertical can be together in the same function. Horizontal, let me use a different color. Horizontal and slant can never be in the same function. Never. That's not possible. A rational function cannot have a horizontal and a slant asymptote. I'm going to put this in writing in a minute. Vertical and slant, yes. Yes, yes. So this combination is possible, this combination is possible, this combination is impossible. So I'm going to write horizontal and slant, never together. In a rational function. Let me make it a sentence. So this is carved in stone. A horizontal and a slant will never be in the same rational function. I didn't mention, but remember, a rational function has to have a ratio and x in the denominator. We're going to get to examples in a minute. Okay, so let me give you an example of each in a graph. Horizontal. It's not part of the graph, but it has to be graphed. Let's say y equals 2, and vertical. Let's say x equals 3. So horizontal and vertical can be in the same function. So here's a graph. So what does this mean again? It means that as x increases without bound towards positive infinity, here's what the function is doing. Getting closer and closer, closer and closer, closer and closer to 2. 2. So this is a horizontal asymptote. As x increases without bound, we say, as it goes to infinity, the function value gets closer and closer to 2. It doesn't go up, it doesn't go down, it just gets closer and closer, closer and closer to 2, towards infinity, and also towards negative infinity. As x gets closer and closer to negative infinity, the function values get closer and closer, closer and closer, closer and closer to 2. Not up, not down. Closer and closer, closer and closer to 2. This is a horizontal asymptote. This one. Now let's talk about vertical. Here's an example. The function is undefined here. It does not exist. But the function values get closer and closer, closer and closer to infinity. Doesn't cross, doesn't turn, of course, it will not be a function. So it gets closer and closer, closer and closer to positive infinity. Same on this other side of the asymptote. As x gets closer and closer to 3, the function values get closer and closer, closer and closer to negative infinity. So this is a typical example of a vertical asymptote. We have never seen this before. Polynomials don't have vertical asymptotes. They're always defined. This function does not exist at 3. The function values get closer and closer, on one side to infinity, the other to negative infinity. It can be both sides infinity, it can be both sides negative infinity, or it can be the opposite. This is a vertical asymptote. Polynomials don't have such a thing. They also don't have horizontal asymptotes. Polynomials go to infinity or negative infinity. They don't stop somewhere or get closer and closer to a line. Rational functions can. Okay, now we know how a horizontal asymptote looks like. We know how a vertical asymptote looks like. Let's see how a slant asymptote looks like. So here's an example of a slant asymptote. When we graph functions with asymptotes, we have to graph the asymptotes first. Although they're not part of the graph, they have to be graphed. So here's an example of a slant asymptote. And here's an example of a vertical asymptote. So here's the graph. Notice something very important. When we say asymptotes, or when we talk about asymptotes, the function eventually has to get closer and closer to it. So don't graph something like this. I've seen it. Students graph the vertical asymptote, and then they graph something like this, or away from the asymptote. No. The function, that's why these asymptotes signify the fact that the function gets closer and closer to them. Closer and closer. The same thing here. This is not something like this. No, it approaches the asymptote, gets closer and closer, closer and closer, closer and closer, closer and closer to the asymptotes. Okay, now we know how these asymptotes look like. And there are 3 different types. And we know, what did I do here? What page am I on? 11. No, 12. Okay. Now, 3 types of rational functions. Are there more than 3 types? Yes. We are only going to study 3 types, but there are more. Okay, number 1, number 2, number 3. Number 1, degree n over degree n. Same over same. Example, f of x, x plus 1 over x minus 2. F of x, x squared minus 1 over x squared plus 3x plus 4. Same degree, same degree, same degree, same degree. First degree, second degree, second degree. Type 1. Type 2. Degree n and degree greater than n. More powerful in the denominator. Okay, here's 1 over x. Here's another, 2x over x squared minus 1. Higher degree in the denominator. Last one, degree n plus 1 over degree n. Again, what does this mean? degree 1, degree 2, degree 4, degree 5, degree 3, degree 4. One more, not more than that, exactly one more. So here's an example. 2x squared plus 1 over x. Degree 1, degree 2. Here's another. 3x squared plus 2x over x minus 1. Degree 1, degree 2. What's the difference? Why did I even split them into these three categories? This one has a horizontal asymptote, HA, horizontal asymptote, that is the leading coefficient over the leading coefficient. So the horizontal asymptote is y equals leading coefficient over the leading coefficient. That's characteristic here. Same degree over same degree. What is here? Horizontal asymptote, y equals 0 forever. I don't have to calculate anything. Here I have to calculate. I have to divide the leading coefficient over the leading coefficient, and that's the horizontal asymptote. Here, when the degree is higher in the denominator, no calculation is required. And this one, no horizontal asymptote, slant asymptote. So these are the three categories. These are easy because the leading coefficient over the leading coefficient, easy to calculate. This is always 0. What does this mean? Again, this type is when it approaches a number. This type is when it approaches 0. Here, 0. From this side, or vice versa. And this one is this case. Okay. Now, this is the new piece. What is the new piece? Things that we have not seen before because polynomials don't have any asymptotes, but the rational functions do. So this with the vertical, it's okay. This with the vertical is okay. This with the vertical is okay. But the slant cannot have horizontal. No horizontal. Okay, so we're going to go through the same steps that we went through with polynomials. So let me open the book. And let me see the page. Which page? Page 429. So we're going to open, choose functions, and graph them. We're going to have as many as possible, like we did last time with polynomials. Okay, from 57, as many as we can fit in the next half an hour. We will identify the type, if it's type 1, 2, or 3. And then we will follow the steps and fill in the table and then graph. You choose, or I will. Okay, I will. I would like to start with 58. Is this a rational function? Yes. It is a rational function because it has